Okay, we are discussing about the stress developing thick wall cylinders. Okay, then last class we obtained the two equations to determine the stress developing thick wall cylinders for radial stress and for the hoop stress. Okay, then these two equations we obtain considering the situation the cylinder under internal pressure and external pressure both. Then today, in today's class, we are going to reduce these equations considering cylinder under internal pressure only situation and also the cylinder under external pressure only situation. Okay. Then we are going to discuss shrink fitting, the stress developing compound cylinders in shrink fitting. We are also going to discuss. Okay, shrink fitting is a method of cylinder bow strengthening method. So then in today's class we are going to discuss in detail about this how the cylinder bow is strengthening using string fitting. Okay, let's continue to today's lecture. Okay, last class we obtained these two equations. These are the equation for radial stress developing a thick wall cylinder under internal and external pressure. And this is the hoop stress, that means tangential stress developing a cylinder under internal and external pressure both. Okay, then by substituting the relevant R value, we can calculate the any point the stresses, the tangential stress and the radial stress using these two equations. Okay, the last class we obtained both the equations. Okay, then these equations we can reduce considering the situation internal pressure only situation, and also we can reduce the equation considering the external pressure only situation, because in most of the cases these thick wall cylinders use as a situation where the internal pressure only situation or external pressure only situations. Okay, so these equations I'm going to reduce considering these two situations. Then what happen, cylinder under internal pressure only situation. Okay, cylinder under internal pressure, I will write that PI internal only situations. Okay, then how to reduce these two equations considering that situation. Okay, what happen when the PI only situation? What happen, the PO is equal, P out is equal to 0. P out is equal to 0. So then I'm going to put these terms we can equate to 0. So then the equation can be reduced. The sigma r, I will write the sigma r equation. Sigma r equation we can reduce this kind of format. Sigma r is equal, then a square pi, then this term is equal to 0, p square minus a square minus pi a square b square divided by a square b square divided by b square minus a square into r square. Here the r is the variable. Okay, here r is the variable. Here r is the variable. This r is the variable. So then this equation we can rearrange. Sigma r is equal, I am going to take the a square pi out pi b square minus a square 1 minus b square divided by r square. Okay, and this is the equation we can use to calculate the internal pressure only situation for sigma r. Okay, that means this kind of situation, cylinder under internal pressure only situation. Pi only exists. Okay, the PO is equal to 0. Then again I am going to reduce the sigma t equation. So the sigma t equation we can write in this kind of format by putting the PO is equal to 0, a square pi divided by b square minus a square plus P O is equal to 0, yeah, the Pi A square B square divided by B square minus A square. Then the R square is the variable. R square is the variable. Okay. So then this equation also we can rearrange. Sigma T is equal. I'm going to take A square Pi, the B square minus A square out from this it's a common term. Then 1 plus here P square divided by R square. Okay. And this is the two equations we can use to calculate the tangential stress and the radial stress where the cylinder is subjected to a internal pressure only situation. Okay, internal pressure only situation. Okay, then let me draw the stress how it is vary. Then the maximum stress. Okay, when the cylinder is subjected to an internal pressure only situation, where is the stress is maximized. Okay, where is the stress is maximized. Okay, these are the two equations. These are the two equations when the cylinder is subjected to internal pressure only situation, where the radial stress is maximized. When the radial stress is maximized, when this term, you can see this term always greater than the 1, because the B square R square divided by R square always greater than 1. So then this the multiplication minus this ratio, 1 minus this ratio is always a negative value. In sigma R always a negative value. Sigma R always negative value. So that so always negative value. Then where its magnitude is maximized, where its magnitude is maximized, this ratio become small. Okay, this ratio become small. Then what happen? R is equal. Let's take the this is 2 R is equal A internal radius. Then external radius the B A. What happen? R is equal A. Sigma R is equal A. If you put the R is equal A, that is the maximum value we can obtain in this situation. R is equal A, its maximum. What is the maximum value? A square Pi divided by B square minus A square, 1 minus B square divided by A square. Okay. Then this is the maximum value for the sigma R in this situation. Sigma R is equal. I'm going to reduce this one. The A square. Yeah. I'm going to take A square Pi B square minus A square minus B square divided by A square. We can cut this one, and also this one we can cut with the minus sign. That means the sigma R is equal minus Pi. That means this internal radial stress at the inner surface, that is equal to minus Pi. That means internal pressure. That is the maximum value. That is the internal pressure. Okay, the internal pressure, because it is acting inward to the surface. That means if you take the internal surface, that is acting inward. This internal pressure is acting inward to the considering stress element. That's why it's negative value, because the standard way of marking is outward from the stress element. The positive stress we are marking outward from the stress element, but this is acting inward to the stress element, so that it is a minus. Okay. Then what happened? Sigma R is equal B. This R is equal B. This ratio become 1. Then 1 minus 1 is equal to 0. That means the stress is equal to 0. That the radial stress is equal to 0 when R is equal B situation. Then let me mark these stresses on a stress diagram. Okay. Now stress the core cylinder. I'm going to mark this one. At this point, there is having this kind of variation 1 over r square variation. This is equal to 0. This is how radial stress is vary because it is negative. At this point it is equal to 0. This is the maximum. That maximum is equal to internal pressure. That EI. This is equal to 0. This is how sigma r is vary. This is the variation of sigma r in a radial direction. Okay. When the cylinder subjected to internal pressure only situation. Okay. When cylinder subjected to a internal pressure only situation. Pi. Okay, then let's find the stress, tangential stress. Let's see what happened in tangential stress. This is the equation for tangential stress. What happened when sigma T R is equal A at the internal surface. Okay, again at the internal surface, what happened, this sigma T always the positive value. This one become maximum, this magnitude become maximum when this ratio become high. To become this ratio become high, this one should be minimum. So R become minimum at R is equal A situation. So that R is equal A situation, sigma T is maximized. That maximum value is equal to A square Pi divided by B square minus A square 1 plus B square divided by A square. So let me simplify this equation. Sigma T R is equal A square Pi B square minus A square plus B square divided by A square. Okay, you can cut this one. Sigma T R is equal A is equal Pi A square plus B square divided by B square minus A square. Okay, B square minus A square. You can see this ratio always greater than, that means this ratio always greater than 1, so that you can see develop tangential stress at the inner surface always greater than the internal pressure. So then let me find that sigma T R is equal B situation. Okay, let's find that one. Then what happened, A is equal Pi B square minus A square 1 plus B square divided by B square, that is equal to 2. That means that 2 A square Pi divided by B square divided by A square. Here this time is not equal to 0 like radial stress, it having certain value. Okay, then these stresses also we can mark on this diagram. In this time the developed tangential stress is greater than the internal pressure, so that I will take this kind of question. So then it also having this kind of variation. This is how the sigma T is vary in a radial direction when the cylinder is subjected to internal pressure only situation. This is how sigma T. This is the maximum value, this is the minimum value. Okay, then this is how we are reducing the equation comes in the internal pressure only situation. Okay, then you can see this internal surface is the critical surface when cylinder subjected to internal pressure only situation, because the stresses, both the stresses sigma t and sigma r, both the stresses are maximum at the internal surface. Okay, there's a more possibility to generate the failure starting from the internal surface. So then the developed internal surface stresses, if we take the certain stress element, we can mark in this kind of manner, in this direction, sigma r, in this direction, for consider the infinitely small stress element sigma t. Okay, both the stresses are maximum at this point. Then we can calculate maximum shearing stress developed. Using the principal stress equations, also we are able to calculate the sigma maximum, and also the tau maximum also we can calculate. Okay, the tau maximum is equal sigma t plus sigma r divided by 2, that is equal to, we find the tau maximum. If we substitute these two values in this equation, we are able to calculate the, it will equal to, I will directly write that the answer, pi b square divided by b square minus a square. This is the tau maximum shearing stress developed due to these two normal stresses acting on it. Okay, so keep remember, if there's a maximum stress values are given, we can calculate whether this if there's a failure occur, we can calculate if you know the maximum principal stress and also the maximum shearing stress developed. Okay, these are we are calculating for cylinder and internal pressure only situation. Then let's see how to find the equations for cylinder and external pressure only situation. Okay, so the next one, cylinder under external pressure only situation. Cylinder under PO, only. That means the Pi is equal to 0. Pi is equal to 0. Okay. Then next, these two equations I'm going to reduce. Considering the cylinder under external pressure only situation. Okay, both the equation I'm going to reduce. Okay, then let's take the sigma r. How to reduce for sigma r PO only, the Pi is equal to 0 minus b square PO, b square minus a square minus Pi is equal to 0 minus plus PO a square b square divided by b square minus a square into r is the variable, r square. Okay, r square. For sigma t also we can reduce this equation. Pi is equal to 0 minus b square PO divided by b square minus a square plus P I is equal to 0, that means minus, here it is minus, minus Pi a square b square divided by b square minus a square into r square. So then both the equation we can simplify. Then we can simplify. Let's take the sigma t first. Sigma t is equal, we can take b square out from this one, the minus b square PO I'm going to take out from the, then here remaining minus we are taken, the plus a square divided by r square. Then this is the equation we can use to calculate the tangential stress when the cylinder is subjected to a external pressure only situation. External pressure only situation. Okay, external pressure only situation. So then the sigma r, I'm going to rewrite the sigma r equation also. So I'm going to take minus b square PO divided by b square minus a square out. The 1 minus a square divided by r square. Okay, this is the equation we can use to calculate radial stress when the situation, the cylinder subjected to a internal pressure only situation. Okay, then let me find the maximum, same as in previous. Let me find the maximum and minimum values for this one. Then what happened, sigma r is equal b, sorry, r is equal b situation, that means outer surface, at the outer surface, the radial stress at the outer surface, because 1 minus this ratio, if this ratio become minimum, the entire expression become maximum, so that at the outer the radial stress become maximum, so that that value is equal minus b square PO b square minus a square 1 minus a square divided by b square. That means you can see the b square, a square, we can cut these all of these values. So finally we are remaining with the sigma r is equal b is equal to minus p o. That means at the outer surface, let me draw the outer surface. This is the outer surface. Then the external pressure is equal to external pressure. The developed stress, radial stress, is equal to minus into external pressure. Okay, minus into external pressure. Okay, then what happened when when r is equal a? When r is equal a, so sigma r is equal a situation. R is equal a situation. This ratio become 1. The 1 minus 1 mean 1 minus 1 mean that is equal to the 1 minus 1, that is equal to 0. That means that is equal to 0. That is equal to 0. Okay. So that means this stress is equal to 0. Let me draw this on a diagram. The radial stress I am going to mark at the internal surface, that is equal to 0. Then external surface, that is equal to pressure, external pressure. So there are that variation under this. Okay, this is how the radial stresses vary in this situation. It's a negative value. Always it is a negative. Okay, because that it's a negative value. So then what happened when the sigma t r is equal this ratio, this is also negative, always negative. This but its magnitude is maximum when this ratio become maximum. The ratio become maximum, which having the minimum value for r the minimum at r is equal to, that means the internal surface. At the internal surface, this sigma t is maximum. That is the maximum value is equal minus b square PO divided by b square minus a square. Here at the a square, this 1 plus 1 is 2. That is equal to twice minus b square PO divided by b square minus a square. Okay, then in this situation also the developed tangential stress is greater than the external pressure at the inner surface. Then it's a negative value. Then sigma t r is equal b. Sigma t r is equal b. What happened? Minus b square po, b square minus a square, 1 plus a square divided by b square. Okay, then this one also further we can simplify. Minus po b square plus a square divided by b square minus a square. This one also greater than, the negative value is also greater than external pressure. So that we can mark these two stresses like this. This is how sigma t is vary in this situation. This is how sigma t is vary in this situation. At the internal surface, sigma t is maximum. This is sigma r. Okay. Then this is how we are reducing these equations. You can see in the internal pressure only situation and also the external pressure only situations. I think you all got a very clear idea how this equation and reduce, how it used to in different situations to calculate the developed stresses on thick walled cylinders. Okay, then let's next we are going to discuss another subtopic, the important subtopic related to this thick walled cylinders. Okay, the deformation of thick walled cylinders. Okay, the deformation of thick walled cylinders. Okay, then consider the deformation of the thick walled cylinder. You may remember we obtained the equation. In the last class we obtained the equation. Consider the deformation of the cylinder. What is that equation? Yeah, this one. You may remember this one. Finally, we obtain this differential equation. Consider the deformation of the thick walled cylinder when the cylinder is subjected to internal and external pressure both. Then this solution of this differential equation having this kind of format: ur is equal c1 plus c1 into r plus c2 divided by r. Here by substituting the displacement function, this is how the radial points are displaced when cylinder subject to internal and external pressure. That means when the cylinder subject to external and internal pressure, how this certain point, point displays in a radial direction expressed using this ur function. Okay, by substituting the relevant r value, we can calculate the displacement of radial displacement using this equation. Then this equation I am going to rewrite by putting the c1 and c2 constants. Okay, then in last class also we obtained the c1 and c2 constants. So then I am going to substitute the c1 and c2 constant in this equation to obtain a ur function. Okay, what is our ur function? c1r plus c2 divided by r. Okay, then after substituting the c1 and c2 constants, what are c1 and c2 constants? In the last class we obtained these two equations. Okay, so anyhow, yeah, I'm going to I will directly write the ur equation after substituting the c1 and c2 constants. Okay, ur equations is equal 1 minus nu, position ratio of the material, divided by elastic modulus of the material, a square pi minus the b square po divided by b square minus a square into variable r plus po minus the pi 1 plus nu a square divided into b square divided by e a square minus the b square into r into r. This is the displacement function we obtain. Okay. Then this equation is for cylinder under internal and external pressure both. Okay. By substituting the relevant R value, we can calculate the relevant displacement, relevant radial displacement. Okay. Then this equation also I am going to reduce. Considering cylinder under internal pressure only situation. Okay. First of all, cylinder under internal pressure only. That means the Pi not equal to 0, the Po is equal to 0. P out is equal to 0, P in is not equal to 0. That means I will draw the sketch also. Only the internal pressure exists. Okay. So then the UR equation we can rewrite UR 1 minus nu divided by E, then the PO is equal to 0. A square Pi B square minus A square into R. R is the variable. Okay. Plus here minus Pi 1 plus nu A square B square divided by E A square minus B square into divided by R. Then this is the equation considering cylinder under internal pressure only situation. Well, this is the equation for cylinder under internal pressure only situation. Let's find the U. R is equal A. That means when the cylinder is subject to internal pressure only situation, what is the radial displacement of internal surface? That means you can see that when the cylinder is subject to internal pressure, this is internal surface radially outward because of the stretch, consider the stretch of the cylinder. The amount this stretch we are going to calculate using this equation. Let's see, find when putting the R is equal A, we are able to calculate that one. When putting the R is equal A in this equation, then simplifying, we are getting this equation, the Pia divided by E A square plus B square divided by B square minus A square. I will directly write this equation by putting the here, if you put the for R, if you put the A, we are getting this equation. Okay, we are getting this equation. This is the displacement of internal surface when the cylinder is subject to a internal pressure only situation. Then what happened? Outer surface displacement U R is equal B situation. That equation I am going to directly write. That equation I have obtained that one already. That Pi A square B divided by E B square minus A square. Okay, this is the displacement of outer surface of the cylinder, thick wall cylinder, when it is subjected to a internal pressure only situation. That means this outer surface also is stretched and outward from the radial outward because of the internal pressure. That is small amount, actually in real situation that is very small, that small amount we can calculate using this equation. Okay, then again I am going to consider the cylinder subjected to a external pressure only situation. Okay, when the cylinder is subjected to external pressure only situation, then I am going to obtain I am going to reduce this equation and I am going to obtain the displacement of both the surfaces. Okay, displacement of both the surfaces. Okay, then what happened when the cylinder subject to a external pressure only. That means the PO only exists, the PI is equal to 0. Okay, in this situation I am going to reduce this equation. Then I will direct write that equation by putting the PI is equal 0 in this equation. We are able to obtain that equation. I will directly write that equation minus 1 minus nu b square PO divided by E b square minus a square into variable R plus PO 1 plus nu a square b square divided by E a square minus b square into R. Okay, then this equation also we can consider. Let me draw the diagram also. Then when the cylinder subjected to a external pressure only situation, what happens? These both the surfaces, that means the internal and external surfaces, radially invert. Okay, that means this outward surface also radially move in this kind of manner, radially invert, and also internal surface also, that means the internal diameter also reduces like this because of the deformation of the thick wall cylinder due to the external PO pressure. So then I am going to find these two values. The displacement U R is equal A. U R is equal A I am going to find. That means internal radius. So I will already obtain this equation. I will directly write that one minus 2PO A B square divided by E B square minus A square. Okay. Then for the external surface U R is equal B, by substituting the B in here, these 2 points, we are able to calculate, we are able to obtain this equation. B P naught A square plus B square divided by B square minus A square minus nu divided by E. Okay, then these are the two equations. These are the two equations. These are the two equations representing the displacement of internal and external surfaces when seen subjected to a external pressure only situation. Okay, then these equations are very important when doing the problems. Okay, then another important subtopic we are going to discuss these equations that we can use, and on that subtopic, the shrink fit compound cylinders. Okay, shrink fit compound cylinders. Okay, the stress developed in shrink fit compound cylinders we are going to discuss in this topic. What is meant by the shrink fitting? Okay, shrink fitting. The shrink fitting is a method of cylinder thick wall cylinder strengthening method. Okay, cylinder wall strengthening method. So what happened when the cylinder subject to a especially when cylinder subjected to a very high internal pressure situation, the both tangential stress and the radial stress is maximum at the internal surface. And also especially the sigma t value. Sigma t value is very high, that is also greater than the internal pressure also. So that the sink fitting is a method to distribute these stresses in different layers of the compound cylinders. Okay, then what happened in this, let me draw the actually the objective of the string fitting is to reduce the sigma t. Okay, by reducing the sigma t we can reduce the maximum principal stress develop, and also the maximum shearing stress develop we can reduce. Okay, the objective is to reduce sigma t in string fitting. Okay, then if you take the thick wall cylinder, this develop sigma t we can represent in this kind of graph. No? Already we obtained this graph. This is how the sigma t is vary. This is how sigma t is vary. Okay, sigma t is vary. So then sigma t is actually very high at the internal surface, and also the sigma r also maximum at the internal surface, so that the maximum principal stress develop also very high, and also the maximum shearing stress develop also very high. So there's a more possibility to, if the failure occur, it will start from the internal surface, because the internal surface is the critical surface, because both the stresses are maximum at the internal surface. So that the string fitting is a method to reduce sigma t. Then we can reduce the maximum principal stress develop, and also the maximum shearing stress develop we can minimize. So what happened in string fitting? Then for example, let's take this is the cylinder bow we are going to strengthening. Let's take this the internal cylinder. Then okay, then let's take this is the cylinder outer diameter. This outer diameter, let's take that is equal to d plus delta. Okay, the delta mean the shrink fitting tolerance. Okay, shrink fitting tolerance, that is depend on the material and also the dimension. Okay, then another cylinder, outer cylinder is like this. The finishes as like this. Outer cylinder, that internal diameter is equal to closer to this value, this diameter, but that is equal to d. Okay, that is equal to d. So then we can see the two cylinders. This is called internal cylinder, this is called external cylinder. The two cylinders, but in different dimensions at normal temperatures. We can't insert this cylinder into this bow, because this diameter is smaller than this diameter, outward diameter. Okay, so that what we are doing in string fitting, we are placing this there's a two method we can use. We can place this internal smaller diameter cylinder in a dry ice. Okay, when it place on a dry ice, what happen? It cool and it shrink, this diameter shrink less than the d. So then we can easily take and insert into this outer cylinder bow. So then when it comes to room temperature, it expand and develop the pressure. Okay, rigidly fix. Another method, we can heat it up this outer cylinder. Okay, by heating, what happen? That will enlarge. That means that this internal diameter enlarge because of the heating, the thermal expansion. So then we can easily insert this smaller cylinder into this larger diameter cylinder. So then when it comes to room temperature, it will form the rigid bond in between these two cylinders, and also the pressure in the mating surfaces. Okay, this is how this is the sink fitting This is how string fitting is done. Then let's see how the string fitting develop sigma t. Okay. Then what happen when after this is inserting, when it comes to room temperature, I will draw on a same diagram. See the inserted internal cylinder, and this is the internal cylinder bow. Okay, then when it comes to room temperature, for example, if this is cool, when it comes to, because the thermal expansion of the when it comes to room temperature, this outer surface move outward, so this is remains same, so that very high pressure develop at the mating surfaces. This is called interface pressure, P, interface pressure. Okay, interface pressure. It's a residual pressure that remain with the compound cylinders. Okay, so that without loading, it having the residual stress develop. Without loading the compound cylinders, it having the residual stress develop. That means if we can separately consider this internal cylinder, it's like a cylinder under external pressure only situation. If we consider this external cylinder separately, it's like a cylinder under internal pressure only situation. In this situation, the developed stresses we can represent when it is not subjected to a pressure. The developed stresses, because of this mating surface pressure, this negative tangential stress develop at the inner surface, the internal cylinder. It's like this. Okay, negative tangential stress is developed. So then, because of the mating surface pressure, this cylinder like a pressure under internal pressure, so that stress we can represent like this. The radial tangential stress developed something like this. Then you can see when this internal cylinder is subjected to a negative sigma t value. Okay, negative sigma t value. Then what happen when this one become pressurized? That means when the cylinder subjected to internal pressure situation, the increase of sigma t is starting from the negative value. Okay, it's starting from the negative value, so that it can take higher load compared to in this situation, because it is starting from the negative value. It not so that it not reaches to the maximum failure limit, because it is starting from the negative value, because it having the negative residual stress, so that it can take more stresses than in this situation. Because what happened in this situation, there's no starting from the zero. Okay, but in here it is starting from the negative, so it can take more pressure with the lesser use of material. So then I will when this kind of a cylinder subjected to a internal pressure situation, I will draw how stresses are developed, distributed. Then when cylinder subjected to an internal pressure only situation, very high pressure, so that the radial tangential stress we can represent like this. It's starting from the negative. So it increases. Its value is small compared to in this situation, because it is starting with the negative. This is slightly increases. Something like this. You can see these two situations. Actually, what happened in string fitting? The developed tangential stresses distributed into two layers of the two cylinders. rather than increase increase of sigma t in a one single cylinder surface. Okay, this is how the sink fitting is work. This is how sink fitting helps to develop the stress develop in thick walled cylinders. So then let's take next. I think you all got a more clear idea about this one. Then next we are going to calculate mathematical calculation related to this sink fitting. Okay, let's see how to mathematically model this effect using thick walled cylinder equations. Okay, then let me draw this one. Let's take this is the outer cylinder. Here we are going to obtain some mathematical equations related to this sink fitting. Okay, let's take this is the outer cylinder. Okay, then let's take this is the internal cylinder. This is the cylinder we are going to insert in this cylinder bore. Let's take radius. Let's take this radius as r. Then this radius is equal to r plus delta. The delta is the shrink fitting tolerance. Delta is the shrink fitting tolerance. Shrink fitting tolerance. Then let's, after assembling these two cylinders, it will comes to this kind of you can represent after assembling these two cylinders something like this. Okay, then the thick cylinder, internal cylinder. Okay, after assembling these two cylinders, then let's mark these values as A, B, and the C. A, B, C. Okay, that means these displacements are very small. Okay, then if we take after assembling this one, in assembly situation, what can you say about this radius? It remain as it is? No, because of the internal pressure, this internal surface of this cylinder expand. That means internal diameter slightly expand because of the internal mating surface pressure. So that because of the internal mating surface pressure, that means pressure developed in this mating surface pressure, this internal surface of this cylinder expand. So that in this time that value is not equal to r, that is equal to r plus delta 1. R plus delta 1. What can you say about this cylinder? Its outer radius remain as same after assembly? No. Because of the external pressure, this amount shrinkage, the diameter shrinkage. Okay, diameter reduces. That value is equal to, here this time r plus delta, slightly reduce delta 2. Okay, delta 2. Then we can write the equation. We can write the basic equation. Delta is equal to okay, delta 1 plus delta 2. Okay, that means total deformation developed in both the cylinders is equal to this shrink fit tolerance. That is the amount both these cylinders are both the cylinders deformations. Okay, then delta 1 mean the radial expansion of the inner surface due to the cylinder subjected to a, that means if you take this outer cylinder, it's like a cylinder subjected to a internal pressure only situation. Okay, if you take this cylinder separately, inner cylinder, it's like a cylinder subjected to a external pressure only situation. Cylinder like a external pressure only situation. Okay, so that I'm going to use the displacement equation we obtained in a previously to calculate the delta 1. That means this surface has expand delta 1 distance. That means this is the before string fitting, this is the surface, that is equal to r, but after string fitting that is expand to r plus delta 1. That means amount it expand displace is equal to radial displace is equal to delta 1. Here also the previous is having something like this radius, the previous is having r plus delta radius. Now what happened, it has displaced inward delta 2 amount. Okay, then I'm going to use the displacement equations. Cylinder subject to a external pressure only situation, that means external pressure only situation, external surface displacement, this equation, and also when the cylinder subjected to a internal pressure only situation, internal pressure only situation, the internal surface, this equation, these two equations to calculate the delta. Okay, write in this equation delta. Here the delta 1 amount, delta 1 I'm going to calculate using the displacement functions. I will write that one. The developed interface pressure is equal to P, the P B divided by E B square plus C square minus B square minus nu plus B P divided by E A square plus B square divided by P square minus A square minus nu. Then this is the delta. By making the P into subject in this equation, by making the P into subject, the P into subject we are obtaining this equation. This is the interface pressure, developed interface pressure is a function of elastic mobility of the material and also the string fitting tolerance and these dimensions of the cylinders. This is the developed interface pressure. If we know the developed interface pressure, we can calculate the stress developed, we can easily calculate. Okay, then this is all about the theory relating to this